Hey guys, my name is Trevor Sullivan and welcome back to my video channel. In this video, we're going to continue down our Rust learning path and we're going to be covering data structures inside of Rust. Now, data structures are a very useful construct in most programming languages, whether you're a Java developer, a C# developer, a Python developer, or a Rust developer, a crustacean, then you'll probably know that there's this concept of a struct that allows us to instantiate some kind of object, right? So with Rust, we have the ability to use the struct keyword here, and what this essentially does is it defines a blueprint for a type of object. And those objects or structs can contain a variety of different data fields that allow you to define or describe the attributes or properties of the object that you're creating a blueprint of. So with structs, we can represent any kind of real world type of data. We could represent a server if you're doing some kind of backend programming. We could represent a cloud account and credentials to access that cloud account. We could define a house or a car or a retail store or a boat or any other type of kind of real world object we can describe as a data structure inside of Rust. Now, the struct itself is only going to describe the attributes or properties of the object that it is that we're creating a blueprint of. Once we've created the blueprint itself, we can then instantiate that struct or create an instance of that struct that represents the actual object itself. In engineering terminology, you probably know that a blueprint of a house or a blueprint of a car doesn't represent an actual car. It's simply describing how you could construct a car. But when you instantiate that blueprint, you get an actual car or an actual house if you're looking at plans for a house, right? So data structures in Rust allow us to do essentially that. But there's something else that we need to concern ourselves with. There's really two key concepts that we need to understand when it comes to structs in Rust. First of all, defining the struct itself is simply describing what the object can look like. And when we instantiate the struct, we have a representation of the actual thing. But there's something else known as methods. And so methods are kind of the second concept that we really need to understand fundamentally with data structures, because a method describes some kind of behavior on that data structure. So with a house, for example, maybe the house color is currently red, and then maybe we want to paint the house blue instead of red. So we could define a method or a behavior, which is basically just a function that is bound to that particular instance of a data structure, and that could allow us to paint the house a different color. Or in the case of a car, we could, drive that car. That would be a behavior that we could declare on the vehicle. And we could drive a certain distance, which would alter the miles driven property or attribute of the data structure itself. So we're going to be taking a look at how to define these data structures and then instantiate them in just a moment. But first, before we get into the actual demonstration, please remember to like this video if you learned something new by the end of it. Please subscribe to my channel, as I am an independent content creator, and your subscription really helps me to grow this community. And then also leave a comment below. Let me know what you thought of this video and other topics that you'd like to see, especially related to the Rust programming language. So in any case, let's go ahead and jump in and talk about how to actually define data structures inside of Rust. So as you can see right here in the documentation, the official Rust programming language book here, we have the struct keyword followed by a unique identifier that you as the developer can specify. So maybe you're defining a user construct or a car or a truck or some kind of off-road vehicle. Maybe you're building a game and you have a character that could have a name. It could have a character type. It could have a, health kind of attribute that indicates the number of hit points that the character has. Maybe certain types of characters, like a warrior, could have 300 hit points, whereas maybe a mage only has 120 hit points. It's really up to you to be creative as the developer to implement these individual data structures. We're just looking at how from a technical standpoint to actually define the data structures in Rust. And then right here inside of our curly braces, we can define the different named fields or attributes or properties, whatever kind of terminology you kind of represent that best mentally. And then we also define the data type of each of these fields in the data structure. So we can have all of the core fundamental data types that are built into Rust that we've previously taken a look at, like Boolean values, string values, integer values, floating point values, and so on and so forth. And then we can instantiate the struct by using the struct in our code and then using curly braces after the name of the struct to specify the initial values for each of the struct fields. And then we can take that entire instance of the data structure and assign it to a variable so that we can reference the different attributes of that struct later on in our code. Now, there are some other advanced concepts that we'll need to understand. For example, in this next example right down here, you'll see that they add the mute keyword. And so adding the mute keyword to a struct variable allows you to mutate the fields of the structure. By default, structs in Rust are immutable, which basically means that once you've initialized the various values of each Rust struct field, you can't actually change the value later on. However, if you use the mute keyword here, then that actually turns the struct instance into a mutable instance, which means that you can mutate the values of the struct fields after you've initialized that data struct instance. Now, if you don't want to make the entire struct mutable, in which case all of these different fields that are defined on the struct in the struct definition right up here, or the blueprint, all of those fields would become mutable if we make a mutable instance of a struct. So if you have only certain fields in your data structure that you want to define as mutable, you can't actually use the mute keyword on each of these struct fields. Rust just simply doesn't support the mute keyword on the individual field level. So instead, the Rust programming language has a built-in core standard data type known as the cell type that allows you to basically wrap a particular data type in a mutable cell, and then you can actually mutate an individual field that's been wrapped with this cell type. But I don't want to complicate things too much for now. Let's actually just jump into our code editor and take a look at some practical examples of defining these data structures. So let's switch over to our editor here. And we're going to add in a new file into our project right here. Let's just call this maybe something like struct sample.rs. Actually, I'll just call it structs, my structs. Let's do mystructs.rs just to make it relatively simple here. I'm not sure why I have a Python file inside of my project here, so let's just get rid of that. And then inside of this mystructs file, we're going to go ahead and define some structs as part of this separate module. Then we'll import this module so that those public structs are accessible from our main.rs file, and then we'll instantiate those from there. So let's start out by creating a public struct, and we'll do a person here, okay? So a person is kind of an object. It's kind of a individual object in the world that's representable by various data fields, right? So typically a person is going to have a first name, and that's typically going to be a string value. A person also typically has a last name as a string value. A person also typically has a birth year. So we could represent that as an unsigned 16-bit integer. And what else do we have? We could also have a month of birth. So birth month, that could be any value from 1 to 12. So for now, I'll just assign it as a U8 to keep things relatively simple. And I think that's probably enough to start with for now. So this is our blueprint of what a person looks like, but it's not an actual person. So what we need to do is to instantiate this person as an object, right? So what we'll do is go ahead and define a function down here. We'll call this pubfn new person. And inside of this function, we're just going to return an instance of person. So then inside of this function, what we'll do is say let p1 equal a person, and we're going to put curly braces directly after the person identifier here because this is how we instantiate a data structure from its blueprint. And then as you can see here, we need to plug in a semicolon at the end, and we'll just return P1. All right, so this is going to allow us to instantiate a person and return that person from this variable back to the caller. So let's go ahead and see what happens if we try to call this from our main RS file. So if we open up the main.rs file right here, go down to the bottom, let's just comment out this code where we were looking at the option type in one of our earlier videos. And now I'm going to say pub mod my structs so that we can access the structs and functions inside of the my structs module. And then we'll say my structs, double colon, and we'll call new person. All right, let's see what happens if we try to execute this code in our terminal. So we'll just say cargo run, and as you can see, we get an error here. So if we go back to this code file where we define the struct and instantiate it, you can see it says missing structure fields. And this is because when we define a data structure and instantiate it, we have to make sure that we specify the initial values for each of the members or fields of that struct. So the way that we do that is inside of these curly braces here, we say, field first name, we'll set that to maybe Trevor, and then call toString to turn it into a string on the heap. And then we'll do a last name of Sullivan and call toString on there as well. Then we'll specify the birth month, and we'll set that to the number 6 to represent June. And then we'll do birth year is 1986. All right, so now that we have initialized all of the fields on this data structure when we instantiate it, the Rust compiler is now going to allow us to execute this code. So if we come back and try to do cargo run, once again, you can see that our program is compiled and executed just fine. But we still have some warnings coming back from the Rust compiler here because we never actually use any of these fields. Yes, we initialize those fields to a certain value, but we're never actually accessing or reading those values back. And so it says all of these fields here are never read. So one option that we have is to specify the attribute. It's an outer attribute called allow, and we can just say allow dead code, and that'll get rid of those warnings because we as developers know that our code doesn't currently reference those values. But another option that we have instead of using the allow dead code attribute is to simply access those values. So what we'll do is say let my person equal the result of this function, and Rust knows that the new person function is returning a person, so we don't have to specify that explicitly in our code because we declared that the new person function is returning an instance of a person. So then we'll do a print line statement here, and we'll go ahead and specify person, well, let's just do first name colon, and then we'll do a 0 placeholder. We'll say last name colon number 1 placeholder, birth month is a 2 placeholder, and birth year is a 3 placeholder. And then in the call to the print line macro right here, we'll go ahead and specify all 4 of these values by accessing the fields from the myPerson variable. So let's do myPerson.first name. Then we'll do myPerson.last name, myPerson.birth month, and myPerson.birth year. And if you're wondering why we're not getting auto completion here, I think that there is a bug inside of the Rust Analyzer extension that doesn't properly recognize these placeholder values. And it looks like we actually have another error here as well. And so this error is actually happening because the default for fields of our data structure are actually private here. So even though in our struct definition here, we made the the struct publicly visible from the module, we also would need to specify that certain data fields in our struct are publicly visible to callers of this module as well. So let's go ahead and specify the pub keyword for each of the fields on our data structure, and that should resolve any compiler issues here. So now if we try to do cargo run, you can see that we get the output first name colon Trevor, last name colon Sullivan, birth month 6, and birth year is 1986. And that also took care of the warning that was indicating that we had some dead code where we were never actually reading the values of these fields here, right? So something else that we could do if we wanted to is just kind of wrap this code in another function here. So let's do pub fn test create person, and we'll go ahead and just paste this code right in here. And because we are defining this function in the same module as the new person function, we'll just remove the reference to my structs as a module, because Rust is automatically going to look for this new person function in the same module where we're calling it. So now we can actually turn this into a private member. So new person can only be called inside the module itself, but then the test create person function is publicly accessible outside of the module. So then we can go back here and say test create person in our main function, and that should effectively have the same result. Sure enough, there you go. So now, rather than actually creating a person inside of the main function and then printing out the values of that person in the main function, now we are just making it a private function here to instantiate the person. And because we're not ever referencing the person from the main module, we can actually make these data fields private. And we can also make the struct itself private. So if we remove the pub keyword from the person struct, we can still run this code, because the only time that the person struct is ever being referenced is from the same module where we defined the blueprint itself. So if you want to kind of self-contain your code all inside of a module and make the struct itself private, but then only expose certain functions that allow you to interact with that struct, then you can just make those individual functions public and keep everything else private inside of your module. And that helps keep your API surface relatively simple and easy to understand by anybody who's consuming your custom module. All right, so that's how we do a basic struct definition. As you can see, we were able to mix and match different data types here inside of our struct. We could also add something like maybe a Boolean data type like visited Europe and say either true or false as a Boolean data type. And so then down here, when we instantiate a person, we'll just say visited Europe is false. And so now we have an extra data field here using a Boolean data type. And of course, it's complaining because we're never actually reading that value. All right, so that is what data structures look like. We could also create other data structures as well. So let's say maybe we want to create a vehicle data structure here that represents a car, a typical car. So then if we wanted to, we could say manufacturer is of type string. The model is of type string. The year of manufacturing could be, let's say, maybe an unsigned 16-bit integer. And we could also do something like color as a string as well. So now this is yet another custom data structure here that's a vehicle instead. We could do fn new vehicle, and that returns a vehicle type. And then inside of here, we'll say let v1 equal a new vehicle. And we can instantiate all of these fields here. So we'll say manufacturer, maybe Porsche. Then we'll do model is equal to, actually we need to do .toString. The model could be 911.toString. And then the year could be something like a 1991. And the color could be about silver.toString. And then we'll terminate that with a semicolon and return v1. Now, in the case of certain types of fields, for example, the color right over here, rather than just making the color an arbitrary string value, we can actually use custom enumeration types in order to specify the valid values for that particular field. So up here, I'll call this vehicle color, and then we can say silver, we could have maybe blue, we could have, red, we could have black, we could have white, we could have maybe green, and that's a pretty good set of colors, right? So now, rather than setting the color to just an arbitrary string where we could have a valid color being goblin, right? Well, that doesn't really make much sense. Goblin is not actually a color. So what we can do is restrict the color of our vehicle to the vehicle color enumeration type. So if we say vehicle color, now we have to specify a valid color from our enumeration. So we could say vehicle color and then say : silver. And now we've initialized the color to silver. But if we try to access goblin, goblin is not a valid color for the vehicle. So we can do any valid value from the enumeration here, but we can't set it to an arbitrary string value. So oftentimes declaring your own custom enumerations for things like vehicle colors, or earlier I used something like a character type. So we could do a character type of, mage, warrior, wizard, and archer, right? So these are the different valid character types that we could have for a character struct that we could define for a game as well. All right, so those are a couple of different examples of defining data structures, instantiating the data structures, and then accessing the members of those data structures. Now, one thing that you'll often want to do is to be able to simply print the value of a data structure. And previously what we did is we used the print line macro right here in order to pass in these individual data fields, because Rust doesn't know how to take a custom data structure and turn it into a string representation. Or does it? Well, if we try to do something like, let's do new vehicle, and then we'll say create vehicle here and make that a public function so we can call it from main. Then we'll do a new vehicle and say, let my vehicle equal that new vehicle. And then we'll do a print line macro. We'll do a couple of curly braces here and pass in my vehicle. Well, as you can see right here, we get a Rust compiler error because Rust doesn't know how to take this vehicle custom struct that we instantiated and turn it into a displayable format, right? Well, what you can often do is specify the debug output here, where we just do : inside of our curly braces, but then we still get an error here indicating that our custom vehicle struct data type doesn't implement the trait debug. So therefore, Rust can't convert our vehicle object into a debug representation. However, we can actually go to the vehicle struct right down here, and there is a special attribute in Rust that's built in called derive. And with derive, we can actually specify certain types of objects that we want to be able to automatically debug. But as you can see, our vehicle color enum also does not implement that debug trait. So up here, we can say derive debug, and that will just use the automatic representation of the enumeration right here. Also, you can see that there are certain values that we're never actually using from the enumeration, but if we want to, we could also add the allow dead code attribute right here, and that will ignore those warnings, even though we're not using those particular values from our enumeration right now. But now that we've derived the debug trait for our vehicle and any dependent types like our vehicle color enumeration type here, we have now resolved those errors. And if we come back to our main function and call the, let's do a curly brace here and import test create person and the create vehicle function, come down here and we'll call the create vehicle function, do cargo run. now you can see that we get this debug representation of a vehicle. No, it's not a, certain format that we could specify here if we wanted to, but this is a much easier way of representing an object rather than having to implement our own custom println macro that takes the individual data fields, breaks them down, and inserts them into a string, right? So using that derive debug trait is a really convenient way of representing our data structures so that we can easily print them out and see if they actually look correct to us in our code. And that takes a minimal amount of effort to implement. All right, so now we have defined custom data structures. We've added fields with different data types. And now something else that I wanted to take a look at is a tuple-based struct as well. So what we've done so far is defined a custom data structure, but the data structure is specifying these named fields, right? We have first name, last name, birth year, birth month, visited Europe. On the vehicle, we have manufacturer, model, year, color, etc. But let's say that maybe we wanted to have a custom data structure with a custom name, but rather than having the named data fields here, we could actually just use a tuple as the basis for the struct, and that will allow us to access the fields using 0, 1, 2, 3, etc. So what we can do is say struct and specify the data type. Let's say vehicle2. Or actually, let's call it vehicle tuple. And then rather than specifying our data fields as a series of named fields here, we can simply specify the data types instead. So let's try to represent a vehicle as a tuple data type rather than a named set of fields. So what I'll do for starters is say string and then string again. So that'll be manufacturer and then model. And then let's just do the year of manufacture, and we'll do that as an unsigned 16-bit integer. So this is a really simple way to define a custom struct, but rather than having named fields, we're just representing those fields as a tuple instead. So down here, what we'll do is create a new function called new vehicle tuple, and we'll return a vehicle tuple type from this function. And then we'll say return a vehicle tuple, and then we want to instantiate the values for this as a string u16. So we'll do Hyundai dot to string, and then Elantra dot to string, and then we'll set the year of manufacture to 2015. Put a semicolon at the end there. Of course, we need to call this function. So let's create a public function called create vehicle tuple, and we'll return, well, actually, let's not return any value from that. We'll do pub fn, of course, and then say, let's call new vehicle tuple, and we'll print out the string representation of that using a debug here. So we'll close that off. And then, of course, we need to implement the debug trait. So we'll go up to vehicle tuple and say, derive debug. So then after we call this function from our main function, that's going to call the new vehicle tuple function here, which simply instantiates a new vehicle using its tuple type rather than the vehicle type. And so now we're going to have these individual fields 0, 1, and 2 rather than having names associated with those individual fields. Let's head back over here and we'll import the create vehicle tuple function, and then we'll call that right down here in our main function at the end. So this is what a vehicle tuple looks like when we print out the debug output. It basically just declares it displays, I should say, the struct type, and then it looks like a literal tuple, right? It's just a parentheses surrounding a bunch of values using different data types, because tuples can have different data types. Even though they kind of look like an array, they can actually have different data types inside of them. So that's how we can create a tuple-based struct as well, in addition to structs with named fields. Now, most of the time, I personally don't really like the tuple-based struct, so I think most of the time I personally would be using a standard struct where we have named fields, but it's really up to you which format you prefer to use. There are, I'm sure, some use cases where you might have very simple data structures where you don't care about assigning field names, but you can use this structure if you want to. Now, just to show you really quickly how to access the individual members, let's say that we wanted to say manufacturer is 0, and then model is placeholder 1. And then let's pass in, let's pass in the result from this new vehicle. So we'll say let my vehicle equal the result of new vehicle tuple. Actually, I'll call it my vehicle tuple. And then we'll say grab this variable, my vehicle tuple dot 0, and then we'll say my vehicle tuple dot 1, and that's how we access the individual fields from the tuple-based struct. So let's go ahead and run this again, and now we have manufacturer colon Hyundai model colon Elantra. And because we are not using the debug type output, we can actually get rid of, in this particular case, we can comment out that derive attribute on the tuple-based struct, and things still work out here because Rust does know how to take the string data type here for the manufacturer and the string data type for the model of the vehicle and insert that into a format string, right? So because we're accessing the individual data fields rather than relying on Rust to convert the entire tuple-based struct to a string representation, we no longer have to specify that debug attribute on the struct blueprint itself. All right, so this video is getting a little bit long at 31 minutes, but we still have to cover, at the very least, mutable structs, right? So in the examples so far, we're instantiating the struct from its blueprint, but we're not actually changing any values of these structs, right? So let's go back to the person right here. Right now, this is a completely immutable struct. Once all the fields have been instantiated, like right here, then we can't change the values after the fact. So if we were to instantiate the struct p1 and then say p1 dot first name equals Shannon, put a semicolon at the end. Also, it's expecting a type capital S string, not a string pointer. So we'll do dot to string. As you can see, we get an error from the compiler saying cannot mutate immutable variable p1. And that's because the struct is immutable by default. One option that we have is to say let mute p1 be a person. So now once we declare the p1 variable as mutable, we can now mutate the data. And if we do a cargo run down here, you can see that the output says first name Shannon, last name Sullivan, even though we initialized the struct with a value of Trevor, we were able to change that value later on because the entire struct is mutable. And then if I do p1 dot last name equals Jones dot to string, rerun our code right here. Now it says first name Shannon, last name Jones, and everything else just stays the same because we're not mutating those other values like birth month and birth year. So when we use the mute keyword here on a struct instance variable, we are basically making all of the different fields in that data structure mutable or alterable, right? But let's say that we only want to allow certain fields to be mutated. Like let's say we want first name here to be mutable, but last name should not be mutable, right? Well, we can't specify the mute keyword on individual struct fields. So if we come up to person and we say mute first name, you can see that we get an error here because this is not valid syntax. We can't just go up to the struct and say, hey, I want first name to be mutable, right? So what we have in Rust is a special data type in the standard library here. So it's under the standard crate under the cell module. And then the cell module exposes a type called a capital C cell. And when we use this cell data type here, it uses a generic input type. So we can use the cell type to wrap pretty much any type of object in Rust. But we could just wrap a string on the heap for starters here, and that will allow us to make a particular field mutable. But then we have to make sure that anytime that we access that field, we have to basically retrieve the underlying object from the cell rather than just referencing the cell directly, right? And there's a couple of methods on the cell that allow us to accomplish that. If we take a look at implementations down here, we have a set function that allows us to alter the value inside of the cell. And then if we want to retrieve the value, we have this function down here called get that is exposed on the cell data structure itself. And that allows us to retrieve a copy of the contained value. So let's go ahead and take a look at how that works. So we'll wrap the string in the cell type right here. And of course, because this is part of a submodule of the standard crate, we need to go up to the top of our module and say use the cell module, and then import the cell type from the cell module in the standard crate. So then when we come down here and look at first name, we've now resolved that compiler error because we've imported the cell type. And then if we try to run this code, we're probably going to get an error here. And this is happening because it says that the cell string, so a string wrapped in a cell, cannot be formatted with the default formatter. And that's because we actually need to get the underlying type of string rather than the cell itself. So let's head back over to mystructs.rs. We'll find where that error is happening right here. And so for now, let's just comment out these couple of lines right here. And let's take a look at the initialization of the first name field here. So right now, we're just taking a pointer to a string. We're turning it into a capital S string that is owned by the struct itself. And so what we want to do is actually create a cell that wraps this string. So to do that, let's just cut this code and then use cell :from, and we can just paste in our code that creates the string there. So what we're doing is just wrapping our string, capital S string, not a string pointer, inside of this cell object, and that satisfies the data type declaration of the first name field here. So let's go ahead and save this, rerun our code, and as you can see, we're still getting an error here, and this is happening because when we attempt to reference the cell field, so when we call the print line macro here to print out the first name, last name, and all the other fields of the person, you can see that we are referencing the first name field. But now when we access first name, we're accessing a cell, not a string. So in order to get the underlying data from the cell wrapper, we call the get method on the cell. So let's see what's going on here. We have an error with copying the data. Right, so what's going on here is that the string type doesn't support the copy trait. So what's happening is that the cell type is expecting the object to have the copy trait. So in order to fix this, we are going to have to actually turn the type, or that field, from a cell wrapping a string into a cell wrapping a string pointer for now. And when we do that, we also have to explicitly declare our lifetime for that field. And then we also have to declare it at the struct level. So let's declare the p lifetime at the struct level. And then down here, where we return a person from this function, we'll add in the static lifetime, which is basically the life of the program. And then we need to instantiate this field with a string pointer from a cell from a string pointer rather than a cell from a owned string type, right? So down here, now instead of just getting a person back, we have a person with a lifetime specifier. And so now if we call the get function here on the cell, you can see that we're now able to retrieve the person's name. But the key benefit here is that we can actually mutate the value of the first name, but none of the other fields are going to be mutable now. But we can't simply set p1.firstname equal to a different value because it's expecting a cell. So you might say, well, I'm just going to use the same code that we have right here where we do cell from and then a new value like Shannon, right? But once again, we get the message cannot mutate immutable variable p1 because p1 has not been declared as mutable. But we don't want to make p1 mutable because then all of the fields, including things like last name, would then be mutable as well. So what we can actually do in this case, rather than setting the first name field equal to a new value, we can just do firstname.set. And this method on the cell wrapper object is going to allow us to set a new value like Shannon. And then up here, we don't have to worry about using the mute keyword on P1, which would have undesirable effects, specifically making all of our fields mutable values. So now if we run our application again, you can see that we were able to initialize the person's first name as Trevor inside of a cell, but then we were able to use the cell's set method to change the value of the cell without actually having to make the struct mutable. So this is a really nice way to make certain individual fields of your struct mutable without actually having to make the entire struct mutable. And as you can see, if we try to change the value of a different field like last name, it's simply not going to allow us. All right, so that's kind of an introduction to structs, tuple structs, mutable structs, and things of that nature. Also keep in mind that we have the cell type as well that we can use to wrap individual field values in a mutable type, again known as the cell. So I hope that you found this video helpful here, that you learned a whole bunch of concepts. I know we went over a bunch of different things here that aren't necessarily directly related to structs, but it is practical stuff that you're going to come across when you start writing Rust programs. Anyway, again, please leave a like on this video if it helped you. Subscribe to the channel, share a link to this video in the playlist with your family, friends, and professional contacts, and be sure to check in for future videos. Thanks for watching, and we'll see you soon.